Chemical equilibrium is a fundamental concept in chemistry that describes the point at which a chemical reaction proceeds in both the forward and reverse directions at equal rates. At this stage, the concentrations of reactants and products remain stable, not because the reaction has stopped, but because it has reached a dynamic balance. The theory of chemical equilibrium allows scientists to predict how reactions behave under different conditions and is crucial for fields ranging from biochemistry and environmental science to industrial manufacturing. The idea of chemical equilibrium began to take shape in the 19th century, particularly through the work of Norwegian scientists Cato Maximilian Guldberg and Peter Weige. In the 1860s, they formulated the law of mass action, which states that the rate of a chemical reaction is directly proportional to the product of the concentrations of the reactants, each raised to a power corresponding to their coefficients in the balanced equation. This law introduced the concept of an equilibrium constant, denoted as K, which quantifies the ratio of product to reactant concentrations at equilibrium. At equilibrium, the value of K helps determine whether products or reactants are favored. A large K value indicates a reaction that proceeds almost entirely to products, while a small k suggests that reactants dominate. This constant is specific to a particular reaction at a given temperature and does not change unless the temperature itself changes. One of the most important contributions to the understanding of chemical equilibrium came from French chemist Henri Le Chatelier in the late 19th century. Le Chatelier's principle states that if a system at equilibrium is disturbed by changes in concentration, pressure, or temperature, the system will shift its position to counteract the disturbance and restore equilibrium. This principle is used extensively to manipulate chemical reactions, especially in industrial settings such as the Haber process for ammonia synthesis. Chemical equilibrium is not limited to gases or solutions. It applies to all phases of matter and is essential in processes like acid-base reactions, solubility equilibria, and redox reactions. In living systems, equilibrium concepts govern enzyme activity, respiration, and many metabolic pathways, allowing cells to maintain homeostasis. In the environment, equilibria involving carbon dioxide, water, and other gases are central to understanding ocean chemistry and climate change. Understanding chemical equilibrium also means recognizing that not all reactions go to completion. Many reactions are reversible, and the extent to which they proceed depends on initial conditions, energy changes, and interaction with external factors. This realization changed the way chemists approached reaction design and control, shifting the focus from merely producing outcomes to managing and predicting them. The theory of chemical equilibrium provides a framework for understanding how chemical systems behave under a variety of conditions. It is a dynamic, predictive model that plays a crucial role in both theoretical chemistry and real-world applications. From the balanced chemistry in our blood to the controlled reactions in a factory, equilibrium is the invisible balance that holds it all together.